So, welcome back. Today, I would like to investigate a particular hybrid system that has to do with a bouncing ball. So, the idea is that I take a ball and I drop it on a surface, and I would first of all like to model it, and secondly, like to figure out how the ball behaves. And the reason why I want to do this is not necessarily because I really like balls, but because this bouncing ball example holds the key to another little peculiarity of hybrid systems that we should be aware of. So here's the setup. I have a ball. It's h above the ground. Now, what happens in between the bounces? Well, Newton tells me that force is mass times acceleration. Right? And the acceleration is, in fact, negative g, where g is the gravitational constant. So if I let x1 be equal to h, and x2 be equal to h dot, which is what we always do, then what I get is that x dot is this thing, 0, 1, 0, 0, x, which is just the point mass, plus this gravitational force that's pulling it down. Now, let's say that the thing that I'm interested in also is where the ball actually is, how high up it is. So y is going to be 0, 1x. So that is my model of the ball. What happens at the bounces? Well, you could try to model ball deformations and whatnot, but that seems rather complicated. So what we're simply going to say is that these are what's called inelastic bounces, which means that a little bit of the energy is sucked out of the ball every time it bounces. And in fact, what we're going to say is that velocity, this is the velocity. So if the ball is coming down here, hits the ground, then the velocity instantaneously flips. I mean, that's why we have a minus sign there, because the ball instantaneously flips. But we're also scaling it with this gamma constant. So we're making the velocity change direction from downwards to upwards, but a little bit less, which means we lost some energy in the bounce. Well, the position doesn't change at the bounce. So this means that my reset condition is going to be this. This is just encoding this fact that I'm flipping a little bit. I'm flipping my velocity and I'm losing a little bit of energy at the time of the bounce. Okay, so let's see what this bouncing ball hybrid automaton might look like. Well, x dot is ax plus b in this case, not bu, and b is 0 minus g, so this is this forcing term that is gravity. No big deal. Now, what's going to happen is I'm going to switch from that mode to itself when I'm bouncing. And we already saw that the reset condition is this inelastic bounce condition that says that we're losing a little bit of the velocity at the time of the bounce. So that's the reset condition. Now, the guard condition is what? Well, clearly, we're bouncing when we're hitting the ground. So we would like the height to be less than or equal to 0, right? Well, let's see what happens. Here comes the ball. Here's the ground. Now the height is 0. We're switching. And now the first thing we do is we reverse the velocity, meaning we're switching. But hey, wait a second. The height is still less than or equal to 0. The height is still 0. So what we're going to do is we're just going to end up spinning like crazy if we have this guard. So this is not a good guard. Let's get rid of it. Instead, what we need to do is we're going to switch when we come down to the ground, and the velocity is pointing downwards, meaning that h needs to be negative, or less than or equal to 0, and h dot has to be less than or equal to 0, meaning we're facing downwards. Or since h and h dot constitute our state, then the guard should really simply be that x is less than or equal to 0. That's the guard condition. Well, it could be that it's just the height is just 0, but this is really the condition that tells us that it's time to switch. Okay, good. So now we have that. Is this any good? Well, I mean, clearly it's good, it's pretty, and we have guards and resets. But does it model, first of all, faithfully what balls do when they bounce? And secondly, are there reasons why a model like this would cause us to be a little bit nervous? To answer that, we need to figure out what the ball is actually doing if we have this model. So, first of all, we have this system again now. What I would like to know is, what is the output of this system? Well, fast forward, sorry, not forward, reverse 2 weeks, and we go back to linear time invariant systems. We know what the solution to this system is. we know that the output is C times this bad boy here that we call the state transition matrix, which was fancy speak for this matrix exponential, times the initial condition plus C times this rather awkward-looking integral here. Now, all of this is not particularly pleasant, and I remember vividly how we struggled to get through this because there were so many integrals to keep track of here. Now, in this particular case, we're a little bit lucky because this A matrix is what's called nilpotent, because if I take A to the power 2 or 3 or any higher exponential here, then I get 0 out. And that turns out to be quite wonderful for us. Why is that? Well, remember that e to the at is really this infinite sum. This should be a parenthesis here, I apologize. It's at to the power k divided by k factorial. Well, in our case, all the higher order a's are equal to 0. So I get first k is equal to 0, which gives me the identity matrix. Then I get k equals 1, which simply gives me a times t. And then I have all the others, which are equal to 0. So e to the at in this case is simply this matrix. Here is the part that comes from the identity matrix. And since A is simply that times t, I get the t up here. So this is my e to the at, or my state transition matrix. So now I should be able to plug this back into the equation for y and get a rather nice-looking expression. So let's do that. Well, here is C, here is the state transition matrix, here's my initial condition, here's this rather awkward-looking differential equation, integral. Now, we can try to solve that. And if we do that, instead of actually doing the math, I did the math, I encourage you to go home and do that, I'm just going to write down what the solution is. It's going to be h naught times the initial velocity, h dot naught, t minus t naught, and that's then minus g over 2, t minus t naught squared. So this is what the output looks like in between bounces. Good. Now that we have that, let's figure out how long it takes in between bounces. So let's say that we start at 0 o'clock, at height 0. This is when the bounce is about to start, and then we want to know how long this took. We want to know how long it took us to get back to the ground. Well, that's simple. Let's pick a big T and say, well, y at that time t has to be equal to 0. Well, then we plug that in. H naught is equal to 0, so we don't get any term there. We just get h dot 0 times t minus this thing. Or another way of writing it is like this. And you know what? This needs to be equal to 0, because h is 0 there and h is 0 there, which is why we have two solutions. So one solution corresponds to t equal to 0, which is at the beginning of the bounce. And the other solution is when we return down. So this is how long it took me to go from the ground up into the air and then back down to the ground. This is the time in between bounces. Let's compute the accumulated bounce times, just because we find it amusing. Well, the velocity at the beginning, so at the first time, let's say that the velocity is v, right? So then the time of the first bounce, instead of h dot 0, I just plug in v there. I get 2v over g. That's the time of the first bounce. Well, the velocity after the first bounce, well, the reset condition says that I have gamma times v. So, okay, I have a new v here. That's what I'm going to plug into my h dot naught there. That immediately tells me that the time of the second bounce is, well, it's the time of the first bounce plus the time it took for the second bounce. And instead of v, I have v divided by gamma there. So that's how long it took me to perform two bounces. And so forth. This tells me that the time of the nth bounce is given by this 2v over g, which is this term that shows up over and over again. And then every bounce gets this gamma to the power k accumulated. Now, this is what's called a geometric series. And if you look that up, or you happen to know it, if gamma is less than 1, which means that you're not adding energy at the bounce times, this thing will actually, okay, here we have gamma less than 1. This will actually converge in the sense that when n goes to infinity, this thing becomes equal to this expression. Well, now maybe some of you are asking, so what? Well, you shouldn't be asking, so what? Well, what's going on there? This is the time it takes to perform infinitely many bounces. Infinitely many bounces. And this is less than infinity. What that means is this bouncing ball is going to go wah, 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 infinitely many. And there is some time, t infinity here, where this system is just going to grind to a halt. And our model is just going to keep computing bounce after bounce after bounce after bounce, faster and faster and faster. And this is actually a serious problem that causes our system to actually crash. So the ball bounces an infinite numbers of times in finite time. And like I said, this is not just a mathematical curiosity that shows that we can compute geometric series. It means that if I'm simulating it, then my simulation would crash. In fact, I encourage you to write this exact model into your favorite simulator and watch it crash. This also means that if I write down my hybrid system like this, then it's undefined beyond t infinity because it's not clear what's happening beyond there. Time is not allowed to go to infinity, so stability, which says what happens when t goes to infinity, you can't even ask that question because t doesn't go to infinity. What's worse, obviously, is that real balls don't do this. Real balls bounce and after a while and they lay still, right? So this is also an indication that our model is not particularly good. And in fact, this type of phenomenon, where you have infinitely many switches in finite time, is known as the Zeno phenomenon, after the philosopher Zeno that had a tortoise race a hare, and the paradox that Zeno came up with was the fact that the hare never managed to overtake the tortoise. And in the next lecture, we will see, first of all, why the tortoise is able to beat the hare, and what to do about it, meaning how do you make the rabbit overtake the turtle? Well, that, my friends, is the topic of the next lecture.